that cart is placed, say, 4 meters above the reference level. We'll make it like a toy. And let's say the radius is 1 meter. I'd like to know how fast would the cart be going when it's here. So it goes through the loop, has a velocity in this direction. What would be its speed there? Can you guys do that problem? I think you can. So if you paid attention on Thursday, you have access to your notes, you should remember that the total energy here has to equal the total energy here. And we only have 2 kinds of energy: gravitational potential and kinetic. See what you can do with this. I don't want to do this for you. I want you guys to do it, but we don't have that kind of time for me to wait for some of you to come to this. Total energy is pretty straightforward. That's going to be a combination of the 2 forms of energy it could have at either spot. There's the possibility of it having gravitational potential and kinetic at the very top of that ramp. And there's the possibility of it having gravitational potential and kinetic at the top of the loop. If you want to find out how fast it's going, conservation of energy is a good way to do so. It's path independent, which means it doesn't matter if the path is curved or straight. It allows the comparison of 2 points and only requires that you understand the flow of energy. If there is nothing doing work on the system from the outside, then the energy here has to be equal to the energy here. Well, set the reference level, a common reference level for all objects. I've kind of forced your hand there. I really haven't, but I kind of have by telling you that the car starts 4 meters above the lowest point. I've kind of forced your hand. You don't have to use that as the reference level, but why wouldn't you since you were given it? You can pick the reference level to be someplace else, but I'm going to work the problems if the reference level is there. And by doing so, I can put together the fact that when the car is here, it is 2 meters above the reference level. Now, again, I'm going to just go ahead and label this point A, label this point B. I'm going to look at the energy at A, and I'm going to set it equal to the energy at B. Now, don't take this the wrong way, but if you don't write down why I'm doing that, and you're just writing down what I'm doing, and right now just looking blankly at the board, you're wasting your time. I'm doing this because there's nothing taking energy away from the system, so I can set the total energy at one point equal to the total energy of the other. Write that down. Mostly because I don't want to answer that question on Wednesday after school at 8 o'clock at night. I'd rather have that question answered right now. Now, I did not give you the mass of the car, so go with it. There's probably a reason why I didn't. I'm going to start with the recognition that potential energy is mg h minus h naught. If I'm setting the ground to be 0, then I'm 4 meters above the ground, and the ground is the 0. That's the reference level. And I said the cars are starting from rest, so 1/2 m 0 squared. At the top of the loop, the total energy has to be the same. The gravitational is going to be mg times 2 minus 0. 0 being the reference level, the object is 2 meters above that. Why? Because it's 2 radii above. That's how I got the 2 meters. It shouldn't be rocket science. This isn't rocket science yet. I can probably hypothesize that the number on the right that's underlined is going to be less than the number on the left that's underlined, suggesting that that energy had to go someplace else, where the only other thing that's left, kinetic energy. The total energy has to stay the same. The type of energy can change. So as the object loses potential energy, it gains kinetic energy. An object rolls down a ramp. It's losing height, gaining speed. Just another way to think about what we've been doing. And the truth is, there's been forces acting on these objects. Those forces are causing accelerations. Those accelerations are changing the speed of the object, but we can now characterize it from the standpoint of energy. Now that's it. You solve for v. You'll notice there's an m in every term. And because there's an m in every term, they go away. Which leaves me with 40 minus 20 equals 1/2 v squared. Which means v is the root of 40. Right? 6 point what? 3, 4 meters per second. 6 squared is 36, so I'm assuming it's somewhere around there. That was not particularly hard. You guys might have struggled. I know it's been a long time since Thursday. Not particularly hard. But since there was some challenge and you guys need to put some work onto this, tell me how fast it's going when it made it to here. All right? You do that problem. I need to know that you got some, flesh in the game here. I haven't changed the total amount of energy. We've just changed how much of that energy is potential. So I'm still going to have 40 minus 10 equals 1/2 v squared, or v is the root of 60, which is a little more than 7, a little less than 8. Not hard. That's not the question I want to ask. This is just getting us started. Here's the question I want to ask, because this is really where we have to go. I want you to consider at this point, the very bottom. If the car has a mass of, let's go with 2 kilograms, a little toy car, 2 kilograms. What must the normal force be on the car here, just before it goes into the loop? That's the answer I want. Because it combines stuff we did earlier with what we're doing now. And that's what's on the AP exam. And that's what I want you to be able to do. You've done this problem twice now. Do it a third time. But this time, you might also have to look at net force. Talk with the folks at your table. Look back in your notes. Stay on the track, as we've discussed before, and travel in a circular path. So if the force on it is unbalanced when it reaches the bottom there, it's about to travel through a circular path. We've had this problem before. Now, that suggests that at the bottom of the path, there will need to be 2 forces acting on it. There will be a upward normal force, and we'll have downward force of weight. They're going to be unbalanced, and we need to make upwards positive. The car's just going to begin its trip through the loop. That net force has to equal MAC, and in this case, normal minus mg has to equal mv squared over r. Now, the first thing I want to point out to you is if you're looking for ways to improve your work and your speed, kinetic energy is 1/2 mv squared, and you get this term mv squared right here inside the centripetal motion portion of the problem too. Just be looking for that. It can save you time. You can find the velocity by using conservation of energy, but you might be better off just leaving it in terms of v squared, or even mv squared for that matter. But let's work it out. We can get how fast the cars are going, which is what's missing, right? We need this to figure out what that normal force is. Well, we know how to find that. We know that at the very top, the cars are going to have gravitational potential energy and no kinetic. And at the very bottom, the cars are going to have all kinetic energy and no gravitational potential energy because they're at the reference level. So mg times 4 has to equal 1/2 mv squared. Well, between you and me, that means that mv squared equals mg times 8. Right? I'm just going to use that mv squared again. So I have normal minus mg equals mv squared over 1 r, or normal equals mg plus mg times 8, right? Seems to me that the normal force is going to be 9 mg. Any questions about what I did? Go ahead.
One of my questions is, if you do net work,
So in this problem, in order for us to find a force, you'll notice we had to use Newton's law to find a force. We use conservation of energy merely to get the velocity here. But like I said, kind of zooming in on this, at this instant, the normal force is this way, the velocity is that way. That normal force is not doing any work. And if you want to talk about over here, talking about dealing with work, well, the normal force was this way. The car is still moving that way. The normal force doesn't do work under this circumstance. It can't. In fact, the only thing that actually did work was gravity. Gravity did work. It was a downwards force. And it caused the car to change its energy from potential to kinetic. So you could say that gravity did work. But you didn't have sufficient information to calculate work from the information that was given. I never gave you the angle of the track. Because of that, you couldn't use the definition of work to figure out how the weight of the cars changed the energy of the cars using the work energy theorem. So there was no easy way for you to find work here. Now, the truth is, there was an easy way for you to find the work done by gravity. It was the change in kinetic energy of the cars. But you had to use conservation of energy to get that. Done. Just getting started, though. Because these are not the problems I want from you. But since you've seen this one, perhaps this next one will be easier for you to do. And I'm a little nervous about asking this question after what I just saw, but I think we still can. Nope. Do you remember that in one of these problems, there was a minimum speed requirement to successfully pass through a loop? You guys remember that question? All right. I would like to know what minimum height would the car have to be released at to successfully make it through the loop? We did this in class. It's the thing is sitting right there. I could pull it out, put it on the table, and show you. But remember the loop-de-loop with the ball in it? Show that if you don't start it high enough, it doesn't make it through the loop. I'd like you to find that. I'd like my answer in terms of H. I'm sorry, my answer in terms of R, G, and M, where M is the mass of the car, R is the radius of the loop, G is the acceleration of gravity. Now, if you don't know where to begin, I will give you a hint. You're starting with a relationship that has to do with conservation of energy. At least that's what you think you're probably doing. Meaning, this height is probably related to this speed. Would you agree with that? The higher I start it, the faster the cars are going when they reach that top part of the loop. Would everybody agree with that statement? The lower I start it, the slower they're going at that loop. But you also know that there are certain conditions that must be met or the car can't make it through the loop. The unbalanced force has to be equal to mv squared over r. And we've done the problem here where we understand there are certain conditions that have to be met. It can go too fast here and just has an increasing normal force in the track. But if it starts to go too slow, we start to run into problems. To do this problem correctly, and I need you guys to do it, not me. If I do it, you'll just be paying attention barely and just writing stuff down, thinking you'll get it when you go home and study, and that's not going to work. Start here. What is the minimum velocity necessary to make it through the loop? Then use that to figure out how high you have to start the car. It's a two-step process. I'm giving you the order of those steps. The problem starts here. Find V min. You've done this problem before. It's in your notes. If you can't do it from scratch, look it up in your notes. Unless you take terrible notes. Okay, I am a little surprised by my first pass through the room that I'm not seeing more people focus on the fact that there's two forces here. And net force has to equal mv squared over r. I'm not trying to make this hard. You've done this problem before, or maybe you can't do this problem. But this is a force problem. And we have to use V here. Omega wouldn't make any sense. And those two forces are in the same direction. It's, to me, at this point where you should be figuring out what it means to write the word minimum here. If V gets smaller, what happens over here? Only one of these can get smaller. Which one? Which one? Normal. What's the smallest normal can get?
0.
So it seems like that's the minimum. Suggests to me that that has to be true. I know you can cancel the M out. You know why I'm leaving the M, don't you? I hope so. If not, well, what kind of energy do I have there? That's the next part of the problem. I'm going to note that the object has gravitational potential and kinetic. How much gravitational potential? Well, it is located 2r from the ground, it looks like. And it has to be moving with a minimum speed of 1/2 m v min squared. That all has to be true. It's sad that I feel a little bad that I have to do this whole thing. I was hoping to get a little more from you guys. What kind of energy do I have here? Well, it's going to start from rest, so when I consider the two possible forms of energy, I think we're starting at 0. This will have to be mg h minus 0. This amount of energy has to be equal to that amount of energy. So when you put it together, mgh has to equal mg times 2r plus 1/2 m v min squared. Well, m v min squared is mgr. That's it. mgh equals 5/2 mgr. Cancel that out. Five halves r, 2.5 r, just one form. When I wrap up and we look at this from the, kind of a bird's eye view now, you've got gravitational potential, mg h minus h naught. You've got kinetic, 1/2 mv squared. We're going to add to it another form of potential energy. That's elastic potential energy. Comes from springs and elastic bands and rubber bands and stuff. Anything that obeys a Hooke's law restoring force can also store energy. Can't prove this to you today, but I can put, a little bit of information in your ear that if you have a spring and you pull a mass back against that spring, then you are storing energy in the spring mass system. I'm sure you know that if I release the box, the spring will push on the box and shoot the box away. Well, that energy is stored here as elastic potential energy. We have 3 forms of energy this semester that we'll have to talk about. We'll add some to it next semester. We'll take a little more formal derivation of this tomorrow, but you need to practice. That's why you have homework. The roller coaster question that's in your homework is the exact question we worked today. You should work it tonight.